Today's show is sponsored by Xilinx, the world leader in programmable technology. Xilinx field programmable gate arrays give engineers a blank chalkboard on which they can quickly and effectively design products with a high degree of flexibility. Xilinx FPGAs are enabling advanced technologies throughout industries such as consumer electronics, medical, aerospace and defense, and security. Xilinx continues to deliver breakthrough programmable technology to the global market. Xilinx.
From the high-performance analog IC design and manufacturing capital of the world, it's National Semiconductor's Analog by Design show. Here's your host, the guru of analog, the one and only Bob Pease.
And here we go with National Semiconductor's Analog by Design show with Bob Pease as host. And the main topic of the day is going to be what's all this high-speed data transfer stuff. We're going to be doing fast data transfer, both analog and digital. Now, first, I'll introduce Kerry Eskow from Avnet, which is one of our sponsors, and he will tell a little bit more about today's show and introduce one of our guest speakers.
Thank you, Bob. In these sessions, we'll explore the complex and challenging issues surrounding high-speed data transfer and demonstrate how this can be accomplished by examining the problem step by step and block by block. We have with us today the author of High-Speed Digital Design, A Handbook of Black Magic, EDN author, and signal integrity wizard, Dr. Howard Johnson.
And now I'll turn you over to Paul Rako, who will introduce some of our other guests.
Yeah, we have two other guests here. From Xilinx, we have Panch Chandrasekaran. He's marketing manager for the High Speed Connectivity Solutions Group. Panch's background is in analog and mixed signal design. Prior to joining Xilinx, he worked on 2.5 gigabit per second and 10 gigabit per second transceiver chips. He has a MSc from University of Central Florida. On my left, we have my buddy Ian King. He's from the DCS group. Ian, let me look you up here, Senior Systems Engineer. I like that title. At National Semiconductor. He has a bachelor's degree in electrical and electronic engineering from Nottingham Trent University in England. We're going to have a little class on the show with your accent. And he's got 10 years of experience in system and board level design. You'll see that when Howard and he start going over his design here. Currently, he works, of course, on high-speed data converter solutions. Bob, what do we got today?
Okay, well, we're going to be having this in two sections. This month, we'll be bringing out Part 1, things that should work. And next month, about March 28th, we'll be bringing out things that do work and things that don't work, which is slightly perhaps different from things that should work. Now, I'm going to throw this stuff on the floor and bring out the general block diagram that we'll be discussing. We have several block diagrams and pictures to explain the interesting parts of the problem. For instance, you got a signal, you got an A to D converter. Now, in this case, it happens to be a very fast A to D converter. Even with moderate speed A to D converters, you still have to worry about and take care of all these problems. But for high speed, it gets even more challenging. For example, at the input, you don't just feed the signal direct to the A to D converter. At a kilohertz or 100 kilohertz you can, but at high speeds, you really need a buffer amplifier, such as this LMH6550. It's a push-pull amplifier with differential input and push-pull output. Some would call it diff-in, diff-out, but I don't. I prefer to call it push-pull. And this kind of amplifier can provide a well-buffered output to the differential inputs of the A to D converter. Now, some people don't want to have a whole amplifier. They are only doing high-speed AC signals, so they might be happy with just a simple balun. And a balun gives you a balanced transformer input and push-pull output with a single-ended input. This is another way to do it, but we're not going to be talking so much about that today because we don't sell baluns. We'll put that back, and then the question is, what do you have going from the A to D converter to the computer? Well, you might show a wire, you might show 64 lines, or you might show a matched pair of lines, a transmission line, and you need 32 of those to get all these fast signals over toward the computer, which means you have something that really looks like a lot of wires. Now, when you have a very high-speed A to D converter putting out a very large amount of bits per second, what do you do with it? You can't just get it all into the computer because computers cannot accommodate all that much information. So you need something very fast, such as a write-only memory, the WOM, which was originally optimized by Signetics about 1978 or 79. It was done as an April Fool's joke because instead of a read-only memory, we got a write-only memory. And Signetics must have put $50,000 into paying for an advertisement that promotes a product that didn't exist. It was a good, big April Fool's hoax. It's there in full 2 pages and color and everything. It was in probably Electronic Design, an EDN magazine, a long time ago. And you can see my web pages. To find the web pages for the WOM, go to www.national.com/RAP, and we'll tell you where to find the WOM pages. Now, fortunately, we have some high-speed converters, digital chips. It's called an FPGA. And Xilinx has come out with an FPGA called the Virtex 4-LX15, which is suitable for interfacing between a fast data flow and a computer that isn't quite as fast as that.
Yeah, that's just one of the family, right?
That's one of a family of
That's when
fast.
you,
Yeah, we chose to use the LX15 device, but Virtex has a whole range of these things that go from, this is the smallest device in the family, and they ramp it right up.
Yeah.
What's your biggest part there, Pants?
I think it's LX200.
wow.
Now, in addition to all these parts of the system, you really need some careful control of the power supplies because you need all sorts of different voltages and different sequencing of voltages. They have to be very compatible. We have an app note that covers that tells the computer what to do and all the power for these. And you also need, we may have to squash this down a little bit, some software to handle this so that you can analyze all the things going on, all the data coming out. Any questions?
That was a good walkthrough because your thing is a little less intimidating than when you see all this stuff. This is from a recent publication of Ian's board. It's a little intimidating, but that kind of walked us through pretty nice.
Okay, very good. Now, who's talking next? Is it your turn to talk?
You know, one thing
Please.
I always liked about the WOM was the idea that you could take infinite amounts of data and put it nowhere. Although that WOM that came out in '79 wouldn't have been fast enough to take all the information that comes out of this A to D.
You'd have to use 4 WOMs.
You'd have to use a lot of WOMs
Bank
to
switching
get
WOMs,
that to
okay.
work.
But they are non-volatile.
That's true. And you know where the data is. You just can't get at it.
This particular A to D is operating, well, what's the maximum rate that it can go at, Ian? Is
It's 1.5 gigahertz.
1.5 gigahertz. Now, it takes in an I channel. It's designed as a 2-channel A to D, isn't it?
Right, that's correct, yes.
Yeah. So if I put my old block diagram here, this is going to show what goes over to the Xilinx chip. You bring in an I interface and a Q interface. Those are 2 analog inputs into the A to D. It's got 2 halves. A top half that's one A to D converter. Bottom half is completely standalone, separate one. As they come in, your sampling rate's 1,500 megasamples per second. 1,500 mega, that's 1.5 gigasamples per second.
Right.
Is ping pong
And,
between these two?
inside, somehow, it does 2 conversions at a time before it gives you an output. So it's actually going to output 2 words at a time with a clock that's a half-speed clock.
Right.
Now, inside the part, are there actually 2 different A to Ds and it's ping-ponging between them?
Yes, there are, yeah. Yeah, it ping-pongs between the 2. And effectively, you're looking at a demultiplexed output. Yeah, you'll create a 750 megahertz.
So 750 megahertz gets the output rate down to a speed that you can operate with LVDS logic.
That's correct.
The LVDS logic family's been around for a while. I think it's a great family for this particular application. It's got low signal amplitude and it's differential. Both of those things help to reduce interference between this digital communications back to the analog side of the board. I think that was a good choice of yours to use the LVDS driver. Now the Xilinx part that we're going to be dumping data into, of course, has LVDS receivers. Can be equipped with those. Let's put this on here. Slide over a little bit. There we go.
Good.
So we'll be bringing in 16 bits for one channel. That's the 2 8-bit groups. 16 bits for the other channel, both dumping into the LVDS receivers here. Now, the LVDS receivers at this point have terminators on them. You've got to terminate lines. That's how we prevent ringing problems in systems. And it going this fast, it's essential. In fact, this system will be terminated at the vertex end with an internal, built-in, adjustable, programmable, really, 100-ohm differential termination right at the endpoint of the line, right where it belongs. Now, it's not good enough to put the terminator outside the chip. It's got to go right at the bitter end of the line at the die. And your LVDS drivers have probably got terminators on them as well.
Whistle's terminated at
Okay.
the ADC output. That's correct.
All right.
Yep.
Now, once we go into the Vertex chip, its purpose is to absorb a huge block of data. It'll take 4,000 words from each channel, total 8,000 words, which, if I remember right, is only a small fraction of the memory that you could have inside a Vertex part.
You can have quite a bit of memory inside the Vertex part. The part that Ian uses is on the smallish side.
It's just under 100K, I think, total memory available with the block RAMs that are on there.
So you picked a part that was just big enough to do just this test application, not the
Exactly.
largest thing you could have used.
Exactly.
All right.
For Ian's purposes, Ian, what he had to do was take the data from the analog in, get the digital data out of the ADC, and feed it to the computer for analysis through a USB. And for that purposes, Vertex 4 LX15 was sufficient to do what Ian was looking for.
Now, on my block diagram, I shortcutted one thing. I said USB because that's what eventually comes off of your board, but there's another chip in the way. You chose to use a parallel interface from the Vertex part into an existing USB controller and then go from there over to the PC.
That's correct.
And the way the system works, if I understand it right, is you put in some analog signals, they go through the A to D converter, you dump all that stuff into the Vertex chip, and then you stop. You take that 4,000 word data record, you transfer it at low speed across the USB into the computer, and then you can analyze it with some software to determine what was the performance of your A to D converters.
But you're not actually turning off or stopping the signal or sine wave coming in.
No, the same way.
It just keeps running.
keeps running. We
And
actually
the
do.
A-to-D converter keeps running.
Right.
It's just this guy ignores data after it turns into a WOM.
Right.
That's okay.
So it is a WOM in a way.
Well, it's a part-time WOM.
Temporary one.
Good.
Now, after we come out of across the USB connection, we go into a PC, could be any PC, and running in there is some software which we call Wave Vision. Now, that's a national product, is that right?
That's right. It's proprietary national software we developed for the sole purpose of evaluating our data conversion products.
Okay, and that software provides, well, it's got a whole list of things that it does, which we'll see in the lab to learn a little bit more about how to evaluate the performance of an A to D converter.
Sure.
In this application, which of the specs did you have the hardest time with?
I think the main thing we try and aim for is we look at ENOB is the best sort of indicator of an A to D as a first glance.
That's effective number
Effective
of bits.
number of bits. So we're dealing with an 8-bit resolution converter. We want to get as close as we can. The first thing you look at the data sheet is how close do you actually get to that 8 number of bits.
Is that your figure of merit? When you design your A to D system,
Right.
you basically look for the effective number of bits.
That's a good starting point. You also, effective number of bits is actually derived from SINAD, which is the signal-to-noise ratio and distortion performance of the converter. So the ENOB will give you a good indication of how good your signal-to-noise ratio and how good the distortion performance is also.
Now, in doing the ENOB tests, if I understand it right, the way that's done is you put in the purest, best quality sine waves you can make.
Right.
And what comes out in digital form, you'll use an FFT to look at the spectrum of that signal. You window it, do the FFT, and what you're hoping happens is that you see one fundamental frequency, no other noise, no other harmonics.
Right.
So different forms of distortion give you different appearances in that spectrum. If you have nonlinear distortion in the amplifier, it would show up as second, third harmonics showing up in that picture. If you had other interference from other sources, like, I don't know, some other thing like your switching power supply, it may have harmonics that show up in the output if they're affecting the input of the circuit.
Maybe resonances in your board from somewhere. They can,
Possibly you could see resonances. The way that would show up is if you did a sweep test, if you tried it at different sine wave frequencies to see if the response was flat. Now, the Wave Vision software will give you an amplitude, so if you knew you could measure the amplitude going in and compare that with the amplitude going out, then you could look to see if you had flat frequency response going through the system.
Well,
How does clock jitter play into this?
Clock jitter, if we're thinking about the sampling clock, if I have a data waveform I'm trying to sample and I move the clock position around, effectively it's the same thing as if I'd added a certain amount of vertical noise. So if you had random clock jitter in the sampling clock, it shows up as white noise or some kind of noise that's been added to the signal. So that would raise generally the noise floor underneath the spectrum of the signal, but not affect necessarily the amplitude of the different harmonics.
We're going to go over to the lab shortly, but before we go, Paul, what's our next item?
Okay, our sponsor today is Avnet. We're going to have a little break here and learn about Avnet, then we're going to go over to the lab.
You can relieve the stress of time-to-market pressure with a single call to Avnet. We'll help you get your idea off the drawing board and to market quicker and more cost-effectively. Working with Avnet gives you access to highly knowledgeable field applications engineers and the most sophisticated development tools and technical education available. Avnet's deep understanding of National Semiconductor's high-performance analog portfolios, including power, amplifier, interface, and data conversion products, as well as Xilinx FPGAs and CPLDs, allows us to help our customers bring a wide range of performance and cost-sensitive applications to life. So contact Avnet today to find out how you can gain an important competitive advantage in the product development race.
Okay, here we are at the lab segment. I'm going to turn it over to Howard, and he's going to talk a little about what we've got set up for you here today.
The setup in this experiment is just like what we talked about at the table. There's a signal source. It has I and Q channels that come out, sine waves on both channels going into our device here. This is where the sampling takes place inside this box. We have two channels, the Q channel and the I channel, going into this device. Sampling goes to the Vertex chip out on the USB cable around to the laptop, and in the laptop is the Wave Vision software, which we've displayed up here at the top on this large screen where you can see it. Up here on the screen, we see on the right the Q channel display, and on the left of the screen, we see the I channel display over here. We're going to focus on the Q channel on the right first. On this channel, what we're seeing is a frequency display from DC up to 750 megahertz. That's half the sample rate of this system. And at DC, you can see there's a big spike. And then at the fundamental frequency of 398 megahertz, that's where the fundamental is. And the second harmonic shows way up here. The second harmonic is down 50 dB below the fundamental. If we look at the total harmonic distortion numbers, those are shown up on the top right of the screen.
Minus 47.
Minus 47 dB total harmonic distortion. So that's the total power in all the harmonics compared to the fundamental. Now what we don't know at this point, though, is we don't know whether that total harmonic distortion is coming from the sampling system or if it's coming out of the signal source itself. And in order to separate those two things, to see which one is causing the distortion, what we're going to do is Ian has provided a filter. Now this low-pass filter, what's the cutoff frequency for this, Ian?
That's 400 megahertz.
400 megahertz, and it has how many poles in the filter?
Something like 13 poles.
Oh, God.
Unbelievable. So it's a really sharp, low-pass filter cutoff. And the idea is that if there was any second harmonics coming from this signal generator, once they pass through the filter, then they'll be attenuated. So what we should see in the display, if we look at the I channel with the filter on it, showing up here on the left side of our screen, here's the fundamental. The second harmonic is suppressed down more than 60 dB below the fundamental. And Bob, what's the total harmonic distortion now?
THD about minus 58 dB, so it's about 11 dB improvement.
So we made a huge improvement in total harmonic distortion just by adding a filter on our signal source. Now that's a good general principle when they're doing any sort of testing. If you're looking for small amounts of distortion, then you need to figure out where the distortion is coming from. And by partitioning the system into pieces and changing one side or the other, you can begin to make inferences about where distortion is happening.
If you move your signal generator to 800, be sure to change your filter, right?
That's right.
You know,
this would only work with a signal below 400, or actually below, you could go from 200 to 400 with this filter, and it would still do a reasonable job of attenuating all of those harmonics. Now let's look at the board itself. It's down here on the table. Ian has architected this board so that, let's see, these are all the inputs coming in the top. Is that correct?
That's correct, yep.
Okay, and then the USB comes out the bottom.
Off on the bottom. Yep.
You'll notice the board is partitioned into two pieces. The top half is the analog section. That's the A to D converter itself. The bottom half is the digital section. That's the Vertex chip going out to the bottom. You know, I like the way that you have divided this into two sections, analog and digital, well separated, so that that helps us to control crosstalk from one area of the board to the next.
Right, that's correct. And as you see here, as Howard mentioned also, inputs coming in at the top of the board, and along with that we also provide an onboard clock source. This makes it so much easier to evaluate this product without the need to have to provide a second signal generator. All you need is the signal you want to sample and evaluate. So it's really quick and easy, get up and go, plug it in, plug in your source, and off you go. And if we move down the board here, the signal goes into the A to D. We have the LVDS interconnect between the outputs. It drops down into the Vertex 4 device where we latch the data. There's a small pipeline of latches before it hits FIFO memory. The FIFO stores about 4K samples per channel. And then it's the job of our USB controller to take that data and pipe it over the USB cable up to the WaveVision 4 software, where we take the FFT measurement and we see the performance measured for you on the screen.
And where'd you put the power?
The power input is just a power brick, 12 volts DC, and the bottom of the board there. We even give you a power switch, turn the thing on, and if we look down the left-hand side of the board there, is basically a whole strip of power regulators. These include the LM 2734 regulator, and this is a 1 amp switcher, and we provide 1.8, 2.5, and 3.3 volts for the Vertex 4. And as we move to the top, there's a 1.9 volt switcher solely for the ADC converter. And that takes care of all the power solutions.
Of course, power is a very important consideration when you're dealing with ADCs. So I think that'll be a very good topic for our next part of the...
And this is what Howard mentioned about all on one piece of copper for 8 bits, one ground plane for even the switchers, right?
Right.
Yeah,
it's all on the same plane.
connected together with the same ground with an 8-bit converter. That's adequate to get this sort of performance.
Mm-hmm. And then even has switching regulators on the system, so that's great.
Very good. Well, thanks for dropping by, folks, and we hope you learned something too. We learned something too. Bye-bye. We'll be back.